Hi, my name is Revanth Kumar Vennu. Deril and I will be presenting our project today, which is LipFormer, an end-to-end sentence-level lip reading system. LipFormer is inspired from a paper named LipNet, which was published by Yanis, Brendan, Shimon, Nando. The LipFormer project aims to improve speech recognition accuracy for people with hearing impairments. As we all know, speech recognition technology is widely used in our day-to-day lives, but it can still struggle to accurately translate spoken words in noisy environments or for people with hearing impairments. Automatic lip reading systems such as LipFormer have the potential to significantly improve speech recognition accuracy for a wide range of users, including those with hearing impairments or in noisy environments. The LipFormer model is based on deep learning algorithm that can accurately transcribe spoken words by analyzing the movements of speakers' lips. The research paper demonstrated that deep learning models can significantly improve lip reading accuracy in real-world settings. LipFormer builds on this research to create a state-of-the-art lip reading model that can accurately transcribe spoken words in a wide range of scenarios. There were few other papers which introduced new ideas regarding the lip reading systems. The first paper I would like to highlight is lip reading sentences in the wild. The authors propose a new method for lip reading sentences in challenging environments where the speaker's face may not be fully visible, lighting conditions can change, and the background can be complicated. They combined CNNs and RNNs to extract spatial temporal features from mouth videos. Additionally, they introduced a comprehensive dataset of more than 100,000 videos from YouTube for training and evaluating their model. Next, we have lip reading with HCNNs. This paper proposes a fresh method for lip reading that employs Hans conventional neural networks. The author suggested that using HCNNs to capture distinctive features from video sequences of lip movements, which can be utilized for speech recognition. They justify the use of HCNNs by demonstrating their better performance in comparison to the other neural network types on various benchmark datasets. Additionally, they present a new dataset of videos for lip reading in Arabic. Lastly, we have end-to-end visual speech recognition with LSTMs. In this paper, the author presents a novel technique of visual speech recognition that involves utilizing long short-term memories, LSTM networks, in an end-to-end fashion. The proposed method receives input video frames of speaker face and generates a sequence of phonemes that correspond to the speaker words. The author claims that their approach has several benefits over conventional methods that employ handcrafted features and separate classifiers. The end-to-end training of the model eliminates the requirement of manual feature engineering, making the proposed method more efficient. Now let's deep dive into our LipFormer model and let's see how that works. LipFormer is built using TensorFlow and trained on dataset of 1,000 video clips of a person speaking. The model consists of convolutional neural networks to extract features from video frames, followed by recurrent neural network to capture temporal dependencies. This combination of CNN and RNN allows LipFormer to efficiently learn to recognize spoken words from lip movements. LipFormer uses uh, connectionist temporal classification (CTC) loss function to train the model. The CTC loss function enables the model to learn to map the input sequences to the output sequences without requiring alignment between the two. This is important because during speech, the time it takes to say each word varies, and there can be paused or other non-speech uh, sounds between there could be other non-speech sounds between those words. The CTC loss function enables the former to effectively learn to transcribe speech from lip movements even when there are not clear or or there is no direct correspondence between the two. In summary, LipFormer is powerful lip reading model that combines CNNs and RNNs to effectively learn to recognize spoken words from lip movements. The use of CTC loss function during training enables the model to learn the transcribed speech from lip movement without requiring alignment between those two. Now let's talk about the dataset that we have used for this project. The dataset that we have used to train and test the LipFormer model is called the Grid Corpus, which was created specifically for audio-visual speech recognition research. This dataset consists of audio and video recordings of 1,000 sentences spoken by each of 34 talkers. For the LipFormer model data, uh, uh, from for the LipFormer model, data from one speaker was used, which includes 1,000 video sequences and their corresponding sentences. The sentences in grid corpus are phonetically balanced and cover a wide range of phonemes, words, and structures. An example of a sentence from the dataset is place red in a zero nav, and each video sequence consists of 75 frames. Using the grid corpus enables LipFormer to learn to recognize a diverse range of speech sounds and structures, which helps to ensure that the model is capable of accurately transcribing speech in a wide range of real-world scenarios. By training and testing on this dataset, LipFormer can achieve high accuracy in recognizing spoken words uh, from a lip movement. Now, Deril will walk you through about the model architecture, and he will also show you a quick demo of how our system works. Over to you, Deril.
Thank you, Revanth. Going over to the model architecture, we have tried our level best to mimic the original paper so as to produce the similar results. Starting with the first layers, we have a convolution neural network layers, multiple convolution CNN layers, wherein we use 3D CNN layers from the TensorFlow API. The main reason for using 3D CNNs was because our input data is video sequences, so we have to learn both in the space and the time dimension. And after three CNN layers, the network is connected to a couple of bidirectional LSTM layers to capture the temporal dependencies in the video data, both in the forward and forward and backward direction. Although the original paper uses gated recurrent units for their RNN architecture, we wanted to try LSTMs for this because in theory LSTMs tend to remember much better over a particular video sequence than GRUs, and we wanted to test it out if LSTMs gave better results than our GRUs or not. After this CNN and LSTM layer, it is connected to a fully connected dense layer with 40 neurons, and each neuron has a softmax probability function, which gives a probability on the scale of 0 to 1. The reason for it being 40 is we found out in the output dataset, we did a unique character dataset, and we found out there are 40 different unique characters, and these character can be one of a letter or a digit or a space. So since the model predict on a character by character level, at each output we see the probability, and whichever neuron has the highest probability, that character is selected as the character for the word or the sentence. Moving on to results, like Revanth said, we are using the grid corpus dataset for this project. Although the grid corpus dataset has 34 speakers, each speaker having 1,000 videos each, we only used data from one speaker so as to limit the computation, because training on 1,000 videos itself was a very big task. Upon and This was split on a train test scale of 90 to 10%. Thus, we had around 100 videos for testing. Upon testing the model, we got an accuracy of 95% for this data set. That is, out of 100 videos, we had 5 videos sampled miscorrectly. And when I say miscorrectly, there were few words or sentences which the model was not able to predict properly. On the other hand, LipNet achieved an accuracy, the original paper achieved an accuracy of 95.2% on the entire grid corpus dataset. Not just relying on the accuracy, because it can not be the correct metric for the whole project. The authors also introduced a different metric called word error rate, which is nothing but the minimum number of insertion, substitution, or deletion that is required on the predicted data so as to convert it to the original sentence. So our model, we calculated the WER and got an amazing word error rate of 0.83%, and the WER lesser the better. So we had only of 0.83%. We also compared our model to different other traditional lip reading models of the past, which we found from the LipNet paper itself, where they compared as well. And we found that employing the usage of deep learning has significantly improved the accuracy when it comes to lip reading, a very notorious task. And also, we found that the usage of connectionist temporal classification (CTC) loss function was effective in improving the accuracy of the model, indicating it's useful in training deep neural networks for video and audio spatial problems. Now, going on to the demo, I have two video sequences which we can test it out. The first one, let's hear it out first.
Bin green H2, please.
So the author says, so the speaker says bin green H2, please. I have the video sequence loaded here, and the current code is in the type of prediction. So let's give this model a run and see what it predicts. The model takes around 10 seconds to predict. Because it has around 8.5 million parameters, it has which was trained on. So let's give it a few seconds to run. Yep. So the first one is the real text, bin green at H2 please, which we heard, and the prediction is bin green at H2 please as well. Let's try it on a different video. We have this video. Let's maximize.
Place green with R5 soon.
Okay, and let's try to predict this as well. Let me change the video. Let's rerun the model. Yes, so the real text in the video is place green with R5 soon, and the predicted is place green with R5 soon as well. Coming back to the slides, in the future work, we have found out few improvements which we could make. So today in the extraction of lip regions, I mean, given the video sequence, given each video sequence is a very big frame, we have limited and cropped it out only to focus on the lip regions, so as to decrease the training time. Because we're using a generalized grid corpus dataset, we found that all the lips in the all speaker dataset are in the similar position, so we could hard code them out. But in the future, we would like to use a different machine learning model to extract the lip regions. And also, since we trained the entire model only on one speaker, we would like to use all the 34 speakers, that is 34,000 video sequences and alignments, to make the model more generalizable. And once that is done, maybe we also hope to employ it in a real world application wherein we can use our web camera to see if it is able to lip read our live video sequences. So in conclusion, we have found in the all the previous papers that lip reading is actually a very notorious difficult task, both for humans and machines, because a lack of audio also means the lack of context, and it's very difficult to understand what the speaker is actually trying to say. And this model has uses both audio and visual information to generate the transcriptions, which is an improvement over the traditional approaches that rely only on that audio information. The grid corpus is actually a very widely used dataset for benchmarking, and we found this dataset to be very useful when we acknowledge the same in the usage in our project. And we believe the proposed model can also be extended to other languages. Only the training would be different and the dataset would be different, and the architecture should still be able to generalize and predict lip reading from the video sequences. So that is our project. Thank you.